You know that feeling, right? You forget to turn off your car lights and you come back later and they're just slowly dimming out, not just off.
Oh, yeah. Or you hook up a bunch of Christmas lights, say, and they look kind of weak, even with a new battery.
Exactly. There's some hidden physics going on there. It's not just the battery ran out.
Not at all.
So today we're diving deep into something really fundamental. It affects almost every electronic thing you use.
Mm-hmm.
It's the relationship between electromotive force, terminal voltage, and internal resistance. Now, I know that sounds super technical.
It does sound a bit heavy, yeah.
But trust me, stick with us. It's actually going to give you a whole new way of thinking about how power really works.
And our mission here really is to dig into our sources and pull out the key ideas. We want to explain why power sources act the way they do. You know, what's actually powering your gadgets? How's that power delivered?
And why sometimes it feels like you're not getting what you expected.
Exactly. Those often misunderstood bits.
Okay, let's kick things off with electromotive force. Emf for short. Now, it's got force right there in the name.
Which is confusing.
Right, because, and this is the first big twist, it's not actually a force in the physics sense.
That's spot on. It's really crucial to get that. Emf is a specific type of potential difference.
Yeah.
Think of it as the electrical pressure or the maximum voltage a source could provide if you didn't connect anything to it, like its open circuit potential.
So before you draw any energy out of it.
Precisely. And its units are volts, just like regular voltage. What's really cool is how many ways we generate Emf. You've got chemical reactions, like in a battery.
Okay.
Mechanical generators using wind or water, even solar cells turning sunlight straight into voltage.
Wow, okay.
Like a standard car battery, a lead-acid one. Emf comes from these molecular reactions inside. Each electron gets about 2 electron volts of energy, which adds up to roughly 2 volts per cell.
So Emf is like the sticker price, the absolute maximum push the power source says it can provide.
Kind of like the theoretical ideal, yeah.
Yeah. But what about the push we actually get when we, plug something in?
Oh, well, that leads us straight into internal resistance. This is key.
Okay.
Every single voltage source, doesn't matter if it's a tiny watch battery or a huge power plant generator, it has 2 main parts.
Right.
There's the source of electrical energy itself, that's the Emf we just talked about.
Right.
And then there's this internal resistance.
Internal resistance. So resistance inside the source.
Exactly. It's this inherent opposition to the current flowing within the source itself. You just can't avoid it.
Why not?
Because the very stuff, the chemicals in a battery, the wires in a generator, the things that create the Emf, they also naturally resist the flow of electricity to some extent.
Okay, that makes sense. And this internal resistance, it explains something I've wondered about, like a big 12-volt truck battery. It's physically way bigger than a 12-volt motorcycle battery.
Mm-hmm.
They both say 12 volts, same F, right? But that truck battery can crank out way more current to start a big engine. Why? Is it just bigger?
It's not just size for show, although size is related. The truck battery can deliver more current because its construction gives it a smaller internal resistance.
Okay. Less resistance inside.
Exactly.
Okay.
And here's a really important point. For the same Emf, the lower the internal resistance, the more current, and therefore more power, the source can actually deliver to the outside world.
Got it. So this hidden resistance, how does it actually affect the voltage we measure, like at the terminals of the battery?
Right, the voltage you can actually use.
Yeah. So what does this mean for the power we actually get? That must be where terminal voltage fits in.
Precisely. Terminal voltage. That's the voltage you actually measure across the terminals of the device when current is flowing.
Okay, when it's doing work.
Yes.
Mm-hmm.
And there's a really crucial, simple relationship here. The terminal voltage, let's call it V, is equal to the Emf minus the current Li times the internal resistance IR. So VF IR.
V if FIR. Okay, so the voltage you get is the ideal voltage minus a bit that's lost inside the battery itself.
You got it. That R term represents the voltage lost or dropped across the internal resistance due to the current flow.
And that simple equation, wow, it suddenly explains so much.
It really does.
Like those dimming car lights we started with? As a battery gets older or discharges?
Its internal resistance, R, increases.
Right. And if R goes up in that equation, V, E, F, F, R, then V, the terminal voltage, goes down.
Exactly. Which means less voltage, less current, less power gets to the headlights. So they dim gradually. It's not an on-off thing.
It's physics playing out right there. Okay, and what about connecting too many lights, even to a good battery?
Same principle, different variable. If you connect lots of lights in parallel, You're trying to draw a really large current.
So I gets big in the equation.
Right. Even if R is small because the battery is fresh, a very large I makes that R drop significant. So again, the terminal voltage V drops and the lights look dim.
Fascinating. It's all connected.
It really is. And, this is exactly how battery testers work.
Oh, yeah. How so?
Well, they deliberately connect a known resistor, a small load, to the battery. This makes it draw a specific current.
Okay.
Then they measure the terminal voltage under that load. If V drops significantly compared to the Emf, it means R, the internal resistance, must be high.
And that tells you the battery is weak or getting old.
Precisely.
Okay, but here's a thought. Does that equation, VMFAR, always hold? Can V, the terminal voltage, ever be bigger than the Emf? That seems weird, like getting more than the maximum.
It does seem weird at first, but yes, absolutely it can.
Ow.
It happens when you're charging a battery.
Okay, when you're putting energy in.
Exactly. When you charge a rechargeable battery, you're forcing current to flow backwards into the positive terminal, opposite direction to when it's discharging.
Right.
So in our equation, VMFAR, the current I is effectively negative when charging because of its direction.
Okay, so minus a negative number.
Becomes a positive. So the terminal voltage becomes V equals an FF plus IR. The voltage you measure across the terminals while charging has to be greater than the battery's own Emf. The charger needs that higher voltage push to force the current backwards against the battery's natural tendency and reverse those chemical reactions.
Like pushing water back uphill into a reservoir.
That's a great analogy, yeah.
Okay, this is making sense now. What happens when we start combining power sources, like putting multiple batteries together in a device?
Good question. How do these principles scale up?
Yeah. Is it just simple addition? Well, it depends how you connect them. Let's talk about connecting them in series first. Like in a typical flashlight with multiple cells end to end.
Okay, positive to negative, positive to negative.
Exactly. When voltage sources are in series, their Emfs just add up algebraically. So two 1.5 volt batteries in series give you a total Emf of 3 volts. Great for getting higher voltage.
Seems straightforward. Any downsides?
Yes. And it's that pesky internal resistance again. When sources are in series, their internal resistances also add up.
Oh, okay. So more cells means more total internal resistance. Right. Which can be a problem. One of the authors whose work we looked at mentioned owning a classic car, a 1957 MGA.
Cool car.
Yeah, but apparently it used two 6-volt batteries connected in series to get 12 volts instead of a single 12-volt battery.
Why would they do that?
Good question. Maybe packaging or cost back then. But the result was a fairly large total internal resistance from adding the two together. And that apparently caused a lot of headaches with starting the car.
Because the high internal resistance limited the current it could deliver to the starter motor. V, like MFEIR again?
You got it. High R car means low V when is large, like during starting.
Okay, so series gives more voltage, but potentially more internal resistance problems. What about connecting them side by side, in parallel?
Right, parallel connections. This is usually done with sources that have the same Emf. Think of connecting the positive terminals together and the negative terminals together.
Okay, what happens then? Does the Emf add up?
No. Interestingly, in parallel, if the Emfs are identical, the total Emf of the combination stays the same as one individual source.
So two 12-volt batteries in parallel still only give you 12 volts.
That's right. 12 volts total Emf.
Then what's the advantage?
The advantage is in the internal resistance and the current capability. When you connect identical sources in parallel, the total internal resistance actually decreases. It's like providing more pathways for the current to flow within the combined source.
Oh, interesting. Lower total R.
Yes. And because the total R is lower, the parallel combination can deliver a much larger total current I before the terminal voltage V drops too much.
I see. So same voltage, but more current capacity.
Exactly. That's why some big diesel trucks, for instance, use two 12-volt batteries wired in parallel.
Right. They still need 12 volts to run everything.
But they need a massive amount of current to turn over that heavy diesel engine, especially when it's cold. The parallel batteries can deliver that huge current because their combined internal resistance is lower.
That's brilliant. It's amazing how these simple series and parallel rules scale up. And it's not just in cars and trucks, is it? You mentioned these principles show up elsewhere.
Oh, absolutely. Nature figured this out long ago. Take the electric eel.
Whoa, okay. How does that work?
It's fascinating. They have specialized biological cells called electroplaques. Think of them as tiny biological batteries. And each one only produces a small voltage, maybe 0.15 volts. Tiny on its own. but the eel arranges thousands of these electroplaques in both series and parallel.
Both? How?
Yeah. So, for example, the South American electric eel might have something like 140 rows of these cells, and within each row there could be 5,000 electroplaques connected in series.
Okay, so 5,000 times 0.15 volts in series. That's a lot of
It
volts.
is. That series connection builds up a huge EMF, maybe around 600 volts.
Wow.
And then having multiple rows, like 140 of them,
Yeah.
effectively in parallel, allows it to deliver a significant current too, maybe up to 1 amp. That combination of high voltage and decent current is definitely enough to stun or kill its prey,
Nature's power pack. That's incredible.
isn't it? And it's not just eels. Other animals like sharks, rays, platypuses, they use similar electrosensory systems, maybe not for stunning prey, but for detecting the incredibly weak electric fields produced by other animals.
Amazing biological engineering. And bringing it back to human technology, we use the same ideas, right? You mentioned solar cells.
Exactly the same logic. An individual solar cell, a photovoltaic cell, typically only puts out about half a volt, zero point 0.5 volts.
Not much use on its own for powering a house.
Not at all. So to get useful voltages and currents, solar panels are made by wiring many individual cells together.
Series and parallel again.
Precisely. You wire cells in series to add up their voltages until you reach the desired level, say 12 volts, 24 volts, or much higher for grid systems. And then you can wire multiple series strings in parallel to increase the total current output.
So it's all about combining these small sources, using the principles of Emf terminal voltage, and managing that internal resistance to get the power you need.
That's the essence of it.
Yeah.
Applying these fundamental ideas allows us to build power systems for everything, from tiny sensors to entire cities.
So what we've really unpacked today is that a battery, or any power source really, isn't just this static box of energy you just turn on.
Not at all. It's dynamic.
Yeah, it's a dynamic system. That internal resistance is always there, always shaping the actual voltage and current you get out. It changes everything, how your car starts, how bright your lights are, how fast your phone charges.
Right. It's the reason why the ideal voltage is rarely what you actually measure under load. Understand the interplay EMF, terminal voltage, internal resistance. It just helps make sense of why devices behave the way they do.
And how engineers have to design around these limitations.
Exactly. How they design systems to deliver power effectively, whether it's a simple flashlight, a complex electric grid, or even how they understand these amazing bioelectric systems in nature. It's all connected by these core physics principles.
So the next time you plug something in, or maybe notice your phone seems to be charging a bit slower than it used to.
Or your car is a bit sluggish, starting on a cold morning.
Yeah. What new questions might you ask yourself now about the hidden physics that's actually powering your world?